Welcome year 13, and this is the second lesson on geometric progressions. And in this lesson we're going to focus on calculating the actual sums of a geometric progression. So just a brief outline of what we're going to do today then. So the sum of the first n terms of a geometric series is given by one of these two formulas here. We remember back last time, the first term of a geometric series is given as a. The second term is a multiplied by the common ratio, so AR, then it's AR squared, AR cubed, and so on, all the way up until we get to the nth term, which is given by AR to the power of n minus 1. So, how do we find the sum of a number of terms? Well, the first one is this formula here, so please make a note of this formula here. It's a multiplied by 1 minus r to the power of n on the numerator, all divided by 1 minus r on the denominator. It's the same formula given here, but it's just slightly written differently in the way it's using the sum here. So sigma here means the sum of all the terms from when k equals 0. So if you substitute k equals 0 in there, it'll be r to the power of 0. So again, it'll just be a and then ar all the way up until the one you want. So if I wanted the sum from k equals 0 up to 7, then it includes 0 up until the 8th term, because this is n minus 1. So there would be 8 terms in this sequence, although it's got 7 on top of the sigma. So we're going to focus on this one here. And first of all, we're going to try and show the proof of this geometric series. It's something that's commonly asked for in the exam. So we set it up like this. The sum of n terms is equal to a plus the second term AR, etc., all the way up to the nth term. And we're going to call this equation 1. Now, if I multiply through this equation by r, it will give me the following. It'll give me r times the sum of n term is equal to a times r in this case, plus AR squared. So each term is multiplied by r, and as we can see, these are the ones that I've written down all the way up until the nth term. And if we times the nth term by r, then it'll just become AR to the power of n. And this gives me a second equation to work with. Right, from here then, we simplify this by subtracting equation 2 from equation 1. So the left-hand side here will give me the following. The sum of n terms minus r times the sum of n terms will equal, now going from the top down, it'll be a, and then if we subtract this one, a minus AR squared minus AR squared, they all become 0, etc. So we have the AR to the power of 4, it will subtract that one out, and then this one here would subtract the AR to the power of n minus 1, and then we would be subtracting just the AR to the power of n. So that is how it looks when I subtract equation 2 from equation 1. Now what we need to do is we need to factorize both sides of this equation. So on the left hand side here, we'll take the sum of n terms out. So it'll be 1 minus r in the bracket. On the right hand side here, we'll take the a as the common factor out. So it'll be 1 minus r to the power of n in the bracket. Now to get the sum of n on its own, we need to divide through now by 1 minus r, and this will then give me here that the sum of n terms is equal to a multiplied by 1 minus r to the power of n, all divided by 1 minus r, which is what we required. So that's proved that the sum of n terms is given by that formula. That is something that you really need to focus on practicing. Okay, let's have a look at some examples then to do with this. So a geometric progression has the first term 50 and a common ratio 1.1. So we know that it's going to start off with 50. To get my second term here, I need to multiply it by 1.1. So for part A, we're being asked to write down the first 5 terms of the sequence. So to get the second term, we need to multiply it by the common ratio. To get the third term, we multiply it by the common ratio again, and so on. So we will end up with 55, and then the next term, when we multiply that by 1.1, will give us 60.5, and just keep doing that. So we've got 66.55, and the fifth term will be 73.205. And as you can see, those terms are getting much bigger. Eventually, they will go off to infinity. Right, part B is asking us to calculate the first 20 terms of this geometric series then. So sum of the first 20 terms is equal to, now we're going to need to use that formula now that we've just proved. So it's A, so that's 50, multiplied by 1 minus r, now the common ratio is 1.1, to the power of n. In this case, we've got 20 terms, so that's to the power of 20, and it's all over 1 minus r, so that'll be all over 1 minus 1.1. Now you need to have your calculators to hand now in order to perform these calculations. Okay, so if you haven't, pause the video and then come back to it. Okay, that's exactly how you type it on your calculator, and the sum of the first 20 terms then, once you've worked that out, it gives you 2,863.75, and I've rounded that correct to 2 decimal places. Just have a check on that one for me, please. Okay, so if we have a sequence then that actually goes down, and it goes down, and it, as the values decrease, they tend towards a value of 0. In other words, they get closer and closer to 0, but they never actually reach it. Sequences like this, we call them convergent sequences. So have a look at this here. We start this sequence here with A, which is 4, AR, which is 3.96, AR squared is 3.9204. And we can see that that sequence is a decreasing sequence. Eventually, it will tend towards 0. Right. I'm being asked to calculate some of the first, of the 21st to 78th terms. So I need to come up with a plan for that. I need a plan. So if I found the sum of the first 78 terms, it will include the first term and up to the 20th term as well. Well, I don't want those terms. So the plan would be to work out the sum of the first 78 terms and subtract then the sum of the first 20 terms off it, and then that will leave us with the terms from 21 up to 78. Okay, what do we need? Well, we need A and we need R. In this sequence here, we know that A is 4, but what's R? Well, to find R, we can just divide 3.96 by 4, and that gives us that R is 0.99. And now we can actually work out, using our calculators, those sums. I'm not going to go into that for you on this video because I will run out of time. But that's how we need to be using this. What about this sequence then? How about the sum of the first 999 terms then? Well, what would that look like? Well, the sum of the first 999 terms would have to follow this. It would be A, which is 4, times 1 minus R, which is 0.99, to the power of 999 for the first 999 terms, over 1 minus 0.99. Now, if you work that out now on your calculator, hopefully you will see it gives us a sum of 399.98. What about the sum of the first 9,999 terms? Well, again, it's just a simple arrow back into your calculator to change the power on this one. So just changing the power here to 9,999. And that's over 1 minus 0.99. Hopefully this time you'll see that it equals 400. And if we then go on to this final one here, again, just arrowing back in. I'm not going to write out the full formula for us this time, but if we type that in on our calculators, again, it's 400. This doesn't change. Okay. What I want us to do now is consider part C here, which is evaluating A over 1 minus R. So, A over 1 minus R, well, A is 4, because it's the first term in our series, and R is 0.99. So if we work that out now on our calculator, what do we get? Well, go ahead and do that for me. You should get 400. So what do we notice then? that this gives us the same as the sum of 9,999 terms and the sum of 99,999 terms. They're the same. So using this formula, when we have an infinite number of terms, will help us work it out much quickly. So we can only use this when we have a value that will get us closer to 0. So in other words, a sequence will only converge to a limit if the common ratio of the sequence lies between -1 and +1. In other words, the modulus of R is less than 1. So hopefully then you could see that if you put a number like 100 of some of the first 100 million terms into that sequence, you will still get 400, because each new term that you add on is getting so small that it barely makes an impact on the sum of the series. Adding 0 to anything keeps it the same. We say in this case that the sum to infinity of the series is 400. So the sum to infinity of any series that is a convergent series can be found by dividing A by 1 minus R. And that's a really important result. Okay, so let's see what that's like in practice then. If A equals 2 and R equals a half, find the sum to infinity of this series. Well, if I started with 2 and multiplied that by a half, you could see that this series very quickly becomes this, and it gets smaller. We could see it's going towards 0. But to find the sum of an infinite number of terms, then A is this first term here, 2. The common ratio is R, so it will be 2 over 1 minus a half, which in this case gives us a sum of 4. So adding all those terms together will give us a sum to infinity equal to 4. And the sum to infinity of this series then, well, in this series here, we can see that A is equal to 8. It starts with 8. We need the common ratio. So how do I find that? Well, I could do 2 divided by 8, or 0.5 divided by 2, which is a quarter, or 0.25. So to find the sum to infinity of this series, it's 8 divided by 1 minus 0.25, which gives us a solution of 32 over 3. Okay, that's it for the examples. What I want you to do now is have a look at these two exercises here. The first one focuses on adding a certain number of terms, and the second exercise, 4.3, focuses on using the sum to infinity. I will post solutions on them early next week so that you can check over your work. When you've done that, I have added a couple of checking questions for you to have a go at. I'm running out of time on the video, so have a go at the 2 checking questions on the information, and again, next week I will provide you some solutions to them. So pause the video here, and when you're ready, have a look at the second question. Here it is, and it's from June 2010, this one. Have a go at those and see how you get on. If you've got any questions, please message me. Thank you very much.